Welcome to this structured Class 10 science lecture on the periodic classification of elements. In our surroundings, we see matter present in the form of elements, compounds, and mixtures. Elements are substances containing atoms of only one type. Today, we know of 118 elements, all of which have different properties. Out of these 118, 94 are naturally occurring. As different elements were being discovered, scientists gathered more and more information about their properties. They found it increasingly difficult to study these elements individually. To resolve this complexity, they began looking for some pattern in their properties on the basis of which they could classify such a large number of elements easily. Classification allows us to study elements systematically, group similar ones together, and understand their chemical behaviors. In this lecture, we will examine the historical attempts that paved the way for the modern periodic table. In the year 1817, Johann Wolfgang Dobereiner, a German chemist, tried to arrange elements with similar properties into groups. He identified groups having 3 elements each, which he called triads. Dobereiner showed that when the 3 elements in a triad were written in the order of increasing atomic masses, the atomic mass of the middle element was roughly the average of the atomic masses of the other 2 elements. For example, take the triad consisting of lithium, sodium, and potassium. Lithium has an atomic mass of 6.9, potassium has 39.0, and the average is 22.95. This value is almost exactly the atomic mass of sodium, which is 23.0. However, this classification model had a severe limitation. Dobereiner could identify only 3 triads from the elements known at that time, and the system was not globally applicable. Following Dobereiner, John Newlands, an English scientist, arranged the then-known 56 elements in the order of increasing atomic masses in 1866. He started with the lowest element hydrogen and ended at thorium. Newlands observed that every 8th element had properties similar to those of the first. He compared this to the octaves found in music, where the 8th note resembles the first, sa, re, ga, ma, pa, dha, and I, and back to sa. Therefore, he called it the law of octaves. For instance, the properties of sodium were found to be similar to lithium, and magnesium resembled beryllium. Despite its elegance, the law of octaves was applicable only up to calcium, assumed that only 56 elements existed in nature, and placed dissimilar elements in the same slot to force his table to fit. The main credit for classifying elements goes to Dmitri Ivanovich Mendeleev, a Russian chemist. He was the most important contributor to the early development of the periodic table. Mendeleev examined the relationship between the atomic masses of elements and their physical and chemical properties. When he started his work, 63 elements were known. He wrote the properties of each element on separate cards and sorted them. He observed that most of the elements got a place in a periodic table and were arranged in the order of their increasing atomic masses. This led Mendeleev to formulate the periodic law, which states that the properties of elements are the periodic function of their atomic masses. His table contains vertical columns called groups and horizontal rows called periods. Mendeleev's periodic table had several remarkable achievements. First, he boldly left gaps in his periodic table for elements that were yet to be discovered. Instead of looking at these gaps as defects, Mendeleev confidently predicted the existence and properties of these undiscovered elements. He named them by prefixing a Sanskrit numeral, Eka, to the name of the preceding element in the same group. For example, he predicted Eka-boron, Eka-aluminium, and Eka-silicon. When Sc, Ga, and Gu were discovered later, their properties matched Mendeleev's predictions almost exactly. Furthermore, his system allowed noble gases, when discovered later, to be placed in a completely new group without disturbing the existing table structure, showcasing his layout's extraordinary foresight. Despite its revolutionary structure, Mendeleev's periodic table suffered from 3 major limitations. First, no fixed position could be given to hydrogen in the table because it exhibits properties of both alkali metals and halogens. Second, isotopes of elements, which were discovered much later, posed a severe challenge. Since isotopes have different atomic masses but similar chemical properties, they could not be placed in different slots without breaking the periodic ordering. Third, the atomic masses did not increase in a regular manner in going from one element to the next. For instance, cobalt with atomic mass 58.9 was placed before nickel with atomic mass 58.7, making it impossible to predict how many elements could be discovered between any two. In 1913, Henry Moseley, an English physicist, showed that the atomic number of an element is a far more fundamental property than its atomic mass. Consequently, Mendeleev's periodic law was modified, and atomic number was adopted as the basis of the modern periodic table. The modern periodic law states that properties of elements are a periodic function of their atomic number. The atomic number gives us the number of protons in the nucleus of an atom, which increases by 1 in going from one element to the next. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. Elements in the same group share identical valence configurations, leading to highly predictable chemical properties. Let us examine the periodic trends in the properties of elements, starting with valency. The valency of an element is determined by the number of valence electrons present in the outermost shell of its atom. As we move from left to right across a period, the atomic number increases, and the number of valence electrons increases from 1 to 8. Consequently, the valency first increases from 1 to 4, and then decreases to 0 for noble gases. In contrast, when we move down a group, the number of valence electrons in the outermost shell remains constant. For example, all group 1 elements, hydrogen, lithium, sodium, potassium, have exactly 1 valence electron. Therefore, their valency remains constant at 1 down the group. Next, let us discuss atomic size, which refers to the radius of an atom. The atomic size can be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. Across a period from left to right, the atomic radius decreases. This is because the nuclear charge increases as protons are added, pulling the electrons closer to the nucleus and shrinking the shell. Conversely, down a group from top to bottom, the atomic size increases. This is because new electronic shells are added as we descend, which increases the distance between the outermost electrons and the nucleus, outweighing the increase in nuclear charge. Finally, let us analyze metallic and nonmetallic character. Metallic character refers to the ability of an atom to lose electrons and form positive ions, while nonmetallic character is the ability to gain electrons. Across a period from left to right, the effective nuclear charge increases, making it harder to lose valence electrons. Hence, metallic character decreases while nonmetallic character increases. Down a group, the valence electrons move further from the nucleus due to shell increments. This makes them easier to lose, causing metallic character to increase and nonmetallic character to decrease. In the table, metals are on the left, nonmetals on the right, separated by metalloids. In this comprehensive lecture, we have journeyed through the historical landmarks of classification. Johann Wolfgang Dobereiner group elements in triads based on arithmetic mass means. John Newlands introduced octaves of repeating chemical characteristics resembling musical scales. Dmitri Mendeleev established atomic mass columns, leaving gaps for gallium and germanium. Henry Moseley revolutionized classification by defining atomic number as the core metric. We explored how valence electrons determine valency. Atomic sizes shrink across periods but expand down groups, and metals dominate the left while nonmetals reside on the right. Review these trends to prepare for exams. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension.